Hello, today I will be presenting my analysis of two research articles focused on cognitive distraction and driving performance. I will examine how using a mobile phone, whether handheld or hands-free, affects attention, reaction time, and overall driving safety. The two studies I'll be discussing connect directly to key cognitive theories we've learned, such as limited capacity attention models, dual task inference, and the cognitive load theory, which we'll explore next. Before we dive into the studies, let's review the cognitive theories that form the foundation of both experiments. First, the limited capacity model of attention tells us that the brain can only handle a limited amount of information at once. If two demanding tasks compete for attention, performance suffers. Second, dual task inference describes the performance decline when attention is split between two simultaneous tasks. For example, talking on the phone while driving. Third is the cognitive load theory. This theory explains that mentally demanding tasks consume more cognitive resources, leaving less available for other essential tasks, like detecting brake lights or traffic signs. Together, these theories explain why even hands-free phone conversations can impair driving. Now let's get into the first article I will be discussing. This article is titled The Effect of Mobile Phone Use While Driving on Response Time, Driving Simulator Study. The researchers behind this study are Hussein S. Muhtar, Ahmad Abdul Habar, and Amar A. Muhammad. This first study investigated how different types of mobile phone tasks impact driving reaction time. The researchers asked the question, how do different mobile phone tasks affect driving reaction time? Researchers predicted that tasks requiring more cognitive and motor effort, like sending a text, would produce the longest reaction times. This hypothesis is grounded in the theories we just discussed. Higher cognitive load reduces performance. Now I will go over the methods in this study. 42 participants ranging between 19 to 55 years old drove in a three-screen simulator replicating realistic highway conditions. The independent variable was the type of phone task performed during driving. These included baseline, which was no phone use at all, hand-free calls, handheld calls, reading a text, and sending a text. The dependent variable was reaction time, measured as the time it took participants to respond to a sudden stop signal in the simulator. Each participant completed multiple trials for each task condition, and the average reaction times were calculated for comparison. Next are the results. Shown here are figures 5 and 8 from the article, both displaying the mean reaction time in seconds for all participants. Figure 5 shows the mean reaction times during mobile phone conversations. The x-axis represents task type. This is baseline driving, hands-free call, and handheld call. While the y-axis represents reaction time in seconds. Baseline driving had the fastest reaction time at 0.628 seconds. Phone conversations without holding the phone had a reaction time of 0.876 seconds, and handheld phone conversations were the slowest at 0.934 seconds. Hands-free and handheld calls were slower, but nearly identical, suggesting that it's the distraction itself rather than physically holding the phone that affects reaction time. Figure 8 shows the mean reaction times during texting. The y-axis is the same, while the x-axis represents baseline driving, reading text, and sending text. Baseline driving again is at 0.628 seconds. Reading text slowed reaction time to 1.022 seconds, but the most significant finding was sending text messages, which caused the greatest slowdown, nearly doubling reaction time at 1.278 seconds compared to baseline. Overall, reaction time increased as the task became more complex. Another thing I wanted to note that was mentioned in the article was that older drivers were especially affected, showing that age can amplify the impact of distraction. The authors concluded that mobile phone use, whether hands-free or handheld, significantly impairs driving. Multitasking with cognitively demanding phone tasks can significantly reduce hazard detection speed and slow down reaction time. My second article will be titled Profiles in driver distraction. Effects of cell phone conversation on younger and older drivers. The researchers behind this study were David L. Strayer and Frank A. Drews. The researchers in this study examined how age interacts with cognitive distraction. They asked, are older adults more impaired by hands-free phone conversations? Researchers hypothesized that older drivers would show larger performance declines because aging reduces attentional capacity, leaving fewer cognitive resources to handle driving plus conversation. Now let's move into discussing the methods behind this study. Participants drove in a high-fidelity patrol simulator, simulating highway driving. The first independent variable was age, with the younger adults being between 18 and 25 years old, and the older adults being between 65 and 75 years old. The other independent variable was task types. The first task type was driving only, which is a single task type, and the second task type was driving while talking on a hands-free phone, which is a dual task type. Dependent variables included brake reaction time, following distance, and speed recovery after a pace car suddenly braked. Results were recorded continuously, allowing precise comparisons across age and task conditions. Now let's explore the results of the study. Figure 5 shows the following distance during the 10 seconds after the pace car braked. Time in seconds is on the x-axis, and following distance in the meters is on the y-axis. The 4 lines represent younger and older adults in both single task and dual task conditions. As shown in the graph, dual task participants, those talking on a hands-free phone, maintained larger following distance compared to single task drivers. The younger dual task line nearly overlaps with the older single task line, demonstrating that distraction can impair driving performance to the same extent as aging. This matches the paper's finding that cell phone users kept a 12% greater following distance to compensate for slower reactions. Figure 3 displays braking behavior over the same 10-second period. The x-axis shows the time in seconds, and the y-axis shows percent brake depression. All groups show a sharp braking speed around 1 to 1.5 seconds, but both older and younger dual task drivers show shallower and slower peaks. This indicates delayed and weaker braking responses when distracted. The article reports the drivers using a hands-free phone had 18% slower brake onset times, which aligns with the flatter delayed braking curves in the graph. Altogether, the results show that cognitive distraction, not age alone, is the main factor reducing braking performance. Researchers in this study concluded that hands-free conversations reduce driving performance in both young and older adults. This study, again, highlights the importance of addressing cognitive distraction, not just handheld phone use, in traffic safety policies. For the synthesis and implications, both studies show the same overarching conclusion. Cognitive distraction significantly impairs a driver's ability to respond to hazards, whether the phone is handheld or hands-free. As I mentioned before, results confirm all 3 of the cognitive theories. Paying attention while driving works best when your focus is only on the road. From a human's factors and policy perspective, these studies suggest that banning handheld phones alone is insufficient because the real danger is the divided attention. These are my references, which are the 2 research articles I analyzed as well as the textbook. Thank you for listening.